Okay, so we're going to go over some projectile motion problems. Now, projectile motion problems still use kinematics, so we're still going to use our basic kinematics problems. We're going to use some variation of these 5 equations, and so, but there's a couple of other wrinkles that we're going to be going through, so it makes it a little bit more complicated than just the basic horizontal kinematics that we just got done. So let's just let's throw out a problem there right off the bat, and we'll kind of take a look at this and see how we solve them. And so we'll start with this top one. A ball is kicked horizontally at 8 meters per second from a cliff 80 meters high. How far from the base of the cliff will the stone strike the ground? Okay, so I don't know how the ball turns into a stone, but we'll assume that the ball stays a ball. How's that? Okay, and so one of the things I'm going to suggest is that you get in the habit of drawing pictures of your problems. It's going to be helpful, and there are actually some physics problems we'll get on tests where you have to draw pictures, like free body diagrams and things like that. And so it kind of helps me, at least when I'm doing these, to kind of be able to visualize what's happening if I have a basic picture of what's going on there. So I have this ball that's kicked horizontally from a cliff that's 80 meters high. So let's draw some kind of a rudimentary cliff, and we'll say we know that this is 80 meters high, and then there's a ball sitting right here, and it's kicked horizontally. So that means that it's going in this direction initially, and it's moving at 8.0 meters per second. Okay, and then we want to know how far from the base of the cliff will the ball strike the ground. And so we're looking at some distance here, and x, and this is our question mark here, okay? And so first thing, let's go out there, I'll get something out of the way right away. Kinematics with projectile motion is not really concerned with horizontal velocity, okay? So those are going to be important. They're an important part of the problem, but they're not part of the kinematics equations usually. So just be aware that this isn't really our initial velocity. This is the initial velocity going that way, but with kinematics, for anything that's falling, I'm interested in velocity going in a vertical direction. So that really wouldn't come into the our initial velocity at all for our kinematics equations. So let's see what kind of variables we have. I have this little thing written out here, so I'm going to look at whatever I have here. So one thing I've been given is 80 meters. Okay, so let's start off with that. I have variable s, which is 80 meters. Okay, and then there's another variable you're always given, or at least it's implied in anything that's falling, and that's going to be acceleration. And we know that acceleration due to gravity is going to be negative 9.8 meters over second squared. Okay, so that's kind of handy. What do we want here? We want the horizontal distance. And now one thing to remember is if I have horizontal velocity, well, then I can get horizontal distance by just taking u for my x direction, which is what that is, my horizontal velocity, and multiplying that by time total. And that's kind of important, that last part, so just keep that in mind. That's something that I'm looking for. So since I've been given my horizontal velocity, all I have to do is find time. So it turns out that what I want is, we want t, this is what I want, and I need to have at least one more variable in there somewhere to figure out what I have. And so one other thing that I have, I don't have, let's see, final velocity, but I do have initial velocity, because my initial velocity in the vertical direction, since this is just going straight horizontal, is actually u, which is equal to 0, right? Because it's this horizontal velocity does not affect what happens going down. And so right now I have three of my variables plus the one that I want, and so I can find my equation. What I'm missing, obviously, is final velocity. So here we go. I have right here, I'm missing final, so I'm going to use S is equal to UT plus 1/2 AT squared. So that's pretty simple. S is equal to UT plus 1/2 AT squared. And then I'm going to go ahead and, because I want time, we'll kind of manipulate this. Now, what is the first thing I can say about this? I know that my U is 0, so that kind of actually goes away. And so what I get is S is equal to 1/2 times A times T squared. And since what I want is T, we're going to change this again. I'm going to write 2S is divided by acceleration, and then to get rid of the T squared, I'm going to take the square root of that. It's going to equal my time. Okay, so let's try that. 2 times 80 meters divided by, and we should say that this is a negative number. I should have written that in the first place. You can see that that is falling downwards, so that's negative displacement. So I'll put a little negative sign in there, and then I will divide that by my negative 9.8, and that's meters over second squared. And then I'm going to take the square root of that whole thing. Okay, and that should be pretty simple. 160 divided by 9.8 gives me a time of 1.63 seconds. All right, now that's not my final answer, but that's going to be able to, I'm going to be able to fit that in here to give myself that final answer there. Oops, wait, you know what? That's not quite right, is it? It's actually, I did that wrong, I'm sorry. It should be, that's actually 16.3, I was misreading that, but I did something wrong, didn't I? I forgot that I have to square root that. So when I square root it, it turns out the time is 4.04 seconds. Okay, much better. That seemed like it would take 1.63 seconds would be kind of difficult there. So then we'll put that last part into here to get my answer. So my 8 meters per second times 4.04 seconds is equal to 32 meters, okay? All right. That's a relatively straightforward question. Now, it does seem like an awful lot of the time in physics land, things are being dropped or thrown from cliffs. So there seems to be a lot of cliffs out there in the utopian world of the perfect physics, and along with the fact that there's almost never any air resistance or friction too, which is, it's amazing how often there is a frictionless surface to deal with. Okay, so let's